Hello, my name is Loreto García Tejada and I'm going to present my master thesis titled Apply Machine Learning to Forecast Formula One Race Outcomes. These are the different sections that are going to be presented here. In recent years, machine learning has revolutionized sport analytics, including the world of Formula One. Thanks to powerful computer techniques and lots of data, machine learning algorithms are good to predicting results and making decisions. Pit stops have emerged as a critical element in Formula One, where timing and efficiency can significantly impact driver chances of success. A well-executed pit stop can propel a driver to front run, with fresh tires and optimal positioning, while a poorly timed one can lead to the loss of valuable positions and endanger victory prospects. The goal of this thesis is to create a predictive algorithm that can forecast if a driver should pit on a certain lap in a Formula One race. By analyzing historical race data and exploiting machine learning algorithms, the aim is to create a reliable system that can effectively predict the need of a pit stop, taking into account various race factors. To achieve this, data from multiple seasons will be used, and 3 powerful machine learning algorithms are employed to identify the most effective approach for a pit stop prediction. Input variables play a crucial role in predicting Formula One pit stop, proving critical insights into strategy decision making during races and helping optimize pit stop strategies. These variables have been carefully collected from diverse sources and encompass categorical, numerical, binary, and time-based data. The information includes details about race, individual drivers, and specific lap characteristics. A total of 21 variables have been selected. 2 variables have been used as an output variables. The target variable has pit stop, indicate whether a driver made a pit stop during a specific lap in a race. Is it a binary variable that represents whether a pit stop occurred or did not occur in a particular lap? On the other hand, the variable good pit stop assesses the performance of a pit stop. It indicates whether a pit stop was successful or not based on the change in a driver's position following to the stop. If the position either improved or remained the same after the pit stop, it's considered a positive outcome. Conversely, if the position worsens, it's classified as a non-optimal outcome. Additionally, the data exhibits a high imbalance, as pit stops are relatively infrequent, occurring in only about 3% of all laps. Furthermore, only about half of these pit stops are considered a good pit stop. This data imbalance adds complexity to the pit stop prediction task, requiring carefully handling during model training and evaluation. To ensure the integrity of the data, several steps were undertaken. Firstly, races held under wet conditions were removed, as the dynamics of pit stop differ significantly in such conditions. The dataset also contains information on the driver's status at the end of the race. Drivers who did not finish or were left more than 3 times were removed to maintain the quality of the data. Additionally, information about drivers making more than 4 pit stops during a race, which indicates possible problems during this race, were also included. There were only 2 variables in which there were null values: quali position and driver standing. For missing qualifying data, the starting position was assigned for this value, assuming the drivers did participate in the qualifying. Null driver standing values were replaced with 0, as the drivers had no championship points. To prepare the data for machine learning algorithm, we held categorical variables using one-hot encoding, binary variables remained unchanged, and numerical variables were scaling using the standard scaler. 3 distinct algorithms, random forest, support vector machine, artificial neural network, were employed, each algorithm under experimentation with different configuration and input parameters. The first machine learning algorithm used is random forest. Random forest utilizes multiple decision trees to make predictions and then combines their outcomes to improve accuracy. To optimize its performance, an hyperparameter fitting process was performed, using grid search to explore various configurations. The chosen hyperparameters include the number of trees in the forest, the maximum depth of the tree, and the minimum number of samples required in a split of a node. Additionally, to address class imbalance in the data, the balanced class weight parameter is used, ensuring equal representation of both classes during training. Cross-validation is performed to evaluate the model's ability to generalize the new and unseen data. Next, the support vector machine or SVM algorithm is explored. Similar to random forest, SVM adjusts its parameters to optimal performance. A hyperparameter fitting process was employed using grid search to find the best combination of values. The key parameters include the regularization parameter, which balances margin maximization and classification error, the kernel, determining the decision boundary type, and gamma, controlling the flexibility of the decision boundary. The balanced class weight parameter was employed to handle class imbalance. And as in random forest, cross-validation was used to ensure model generation performance. Finally, artificial neural networks were explored in predicting the target variables. Class weighting was utilized to handle class imbalance effectively. The parameters included the hidden layer configuration, which determines the number of neurons in each hidden layer, the L2 regularization parameter, which prevents overfitting, the dropout rate, reducing overfitting by activating specific neurons, the batch size, impacting the model's convergences, and the number of epochs, representing the training iteration. Early stopping was employed as a regularization technique to prevent overfitting. As before, cross-validation was used to ensure the model ability to generalize the new data and find the best hyperparameter configurations. The results obtained were using the best hyperparameter of each of the algorithms for both of the output variables. Here, I will show only the most relevant results. Upon analyzing the confusion matrix for the past pit-stop variable, we observed that the random forest model correctly identified a large number of instances with pit stops. However, it had a relatively high number of false positives, indicating that the model tended to predict pit stop even when they did not occur on that particular lap. Similarity for the good pit stop variable, this higher false positive may be attributed to the model's inclination to predict the majority class, not optimal pit stop, more frequently. To further evaluate the performance, I calculate metrics such as precision, recall, RF1 score. Precision represents the percentage of true positive predictions among all positive predictions. Recall represents the percentage of true positive predictions among all actual positive instances, and the F1 score is the balance between precision and recall. The random forest classifier achieves a high accuracy value for both variables. However, considering the class imbalance of the data, accuracy might be misleading. The F1 score for both variables are relatively low, indicating that the model's ability to correctly identify instance with pit stop or good pit stop is compromised. In other words, the model struggles to achieve a good balance between minimizing false positive and false negatives. Additionally, I compared the training and validation error to assess the model generalization ability. The training error measures the accuracy of the model of the training data, representing how well the model fits available information. The validation error quantifies the model's ability to generate the new unseen data, providing insights into potential of the fitting. For both variables, the trained random forest demonstrates an exceptionally low training error, indicating a high accuracy fit to the training data. However, a relatively higher validation error, suggesting some challenges in generalizing the model performance of new data. The findings underscore there is still room for improvements in the predictive capabilities of the models for both variables. The SVM algorithm is evaluated in the same manner as the random forest for predicting both variables, as pit stop and good pit stop. The confusion matrix for the variable indicates that the SVM model correctly identifies a significant number of instances with pit stop, but also has some false positives, predicting pit stop that did not occur. The F1 score provides a more informative analysis of the SVM model performance, especially considering the class imbalance of the data. For the has pit stop variable, the precision score suggests that the model can correctly identify classes with pit stop with a reasonable level of confidence. The recall score, it indicates that the model captures a significant portion of the case with pit stop, although there is still room of improvement. The F1 score, which combines precision and recall, provides a balanced assessment of the model's performances. And in this instance, it is relatively high, indicating a better performance in predicting this variable. In contrast, the performance metric for the good pit stop variable reveals some problems. The precision score suggests that the model's prediction of good pit stop may not be as accurate. The recall score indicates that the model ability missed a considerable number of cases with good pit stops, and the F1 score highlights that the model is not able to correctly predict cases with good pit stop. This means that the model struggles to achieve a good balance between minimizing false positive and false negatives for predicting good pit stops. The comparison of the training error and validation error for the target variable used in trained SVM model provides valuable insights into the prospective performance. The relatively high validation error suggests potential change in generalization effectiveness in data, indicating a possible presence of overfitting. Finally, for the neural network, let's start with the result for the has pit stop variable. The loss function, which measures the difference between predicted and actual value for the target value, decreased considerably for both training and test datasets. This reduction in loss indicates that the ANN is effectively relearning from training data and generalizing well-to-seen test data. The F1 scores for the has-pit stop variable also saw promising improvement over the epochs, reaching a value of almost 0.6 in the end of the training. The achieved F1 score indicates that the neural network can correctly identify cases with pit stop with reasonable level of confidence, especially when compared to the result obtained with other algorithms. However, upon closer examination, we observed the presence of some overfitting in the has-pit stop variable model. Despite implementing various measures to address this and improve the model generalizability, the overfitting is evident for the disparity between the performance on the training data, which overperforms the test data. Moving on to the results for the good pit stop variable, we observe a similar trend of the previous variable. The loss decreased over training epoch, indicating successful training from the data. However, the performance for the good pit stop variable is notably worse compared to the has pit stop variable. The overfitting in this model is even more pronounced, with a larger gap between the performance of the training and test data. The F1 score for the good pit stop variable reaches a lower value of 0.36 for the end of the training, indicating that the neural network's ability to correctly identify cases for this variable is relatively limited. In the comparative analysis of these three algorithms, we examined the F1 score achieved using the best combination for both target variables. The results clearly show that SVM overperformed over other algorithms in predicting both pit stop occurrency and good pit stop quality. It achieved the highest F1 score for both variables, indicating its superior performance in capturing the patterns and characteristics of pit stops. While SVM saw the best results, neural network also demonstrated competitive performance, especially for the has-pit stop variable. Random forest, on the other hand, displayed lower F1 score for both variables, suggesting comparative weakness performance in pit stop prediction. For further insight into the model's performance, we utilized the best performing algorithm, SVM, to predict the outcome of the entire race in the going on 2023 season. These figures visualize the pit stop prediction made by the models for each driver and each lap in the first race of the season. The analysis of the algorithm's performance in predicting optimal pit stop timing reveals some interesting patterns. In most cases, the algorithm constantly predicts the optimal time for a pit stop a few laps prior to the actual executions. This suggests that the algorithm is capturing significant indicators and trends in the race data, enabling it to make proactive predictions. However, there is still a specific instance, particularly during the third pit stop for drivers in less favorable positions, where the algorithm fails in to accurately predict the appropriate timing. This discrepancy can be attributed into the unique strategies adopted by the drivers in disadvantaged positions. These drivers may opt for unconventional approaches, taking calculated risks to improve their race outcomes. As a result, the algorithm's predictions might not align with their strategy decisions, leading into incorrect timing predictions. In the remaining cases, the algorithm accurately predicts the exact time for pit stops in some instances, but the majority predicts occur a couple of laps earlier than the actual stop. This suggests that the algorithm has a trendly to anticipate the need of a pit stop a few laps before the ultimate executed. This behavior can be beneficial, improving drivers an ample time to plan and make necessary adjustments in the race strategy. In conclusion, this thesis has explored various hyperparameter configurations to optimize the performance for three machine learning algorithms: random forest, support vector machines, and neural networks. The objective was to predict pit stop in Formula 1 races using historical data from the season spanning 2019 to 2022. The finding for this thesis provide insights into the challenging nature of predicting pit stop in Formula 1 races. Firstly, the results for the has-pit stop variable demonstrate promising potential. The models exhibit reasonable accuracy in predicting whether a driver should make a pit stop during a specific lap. However, it is important to note there is still room for improvement in achieving more predictions. Pit stop prediction is a highly complex task. The interaction of multiple variables and the inherent uncertainties involved make it challenging to capture all the nuances and accurately predict the occurrence of a pit stop. The finding reaffirms that achieving perfect prediction in this area is not realistic. but the model can serve as a value tools to assist the decision-making process. On the other hand, the result for good pit stop variable indicates the inherent difficulty to determining whether a pit stop will result in a favorable outcome for a driver. It is not possible to know with certainty if a pit stop will be successful or not. The team makes the best decision based on the valid information of strategic considerations, but there is no guarantee of a positive outcome. Moreover, the complex nature of Formula One means that if one driver gains position to a pit stop, another driver may lose a position. It's impossible for all drivers to be benefit from a pit stop simultaneously in a race. Therefore, it's important to recognize that the models developed in this study cannot be relied upon solely to accurately predict whether a performance is likely. However, they can serve as a valuable tool to support decision-making process alongside other relevant information and expected knowledge. By incorporating predictions from the models, teams can improve their understanding of pit stop dynamics and make more informed decisions about race strategies. Thank you very much, and any question can be sent to my academic or personal email.